Hello, my name is Piotr Grabowski and I'm a software team leader at ScyllaDB. Today my talk will be about load balancing and all the experiences that we've learned from ScyllaDB drivers, both algorithmic ones, more theoretical ones, as well as different practical benchmarks that we have performed, and we have collected some really interesting data that we are willing to share with you. So first of all, a few things about me. I'm the software team leader at ScyllaDB. My team is responsible for ScyllaDB drivers as well as Kafka connectors, and I have joined ScyllaDB over 3 years ago. So let's start with some basic description of load balancing in ScyllaDB. As you all well know, ScyllaDB is a resilient database, so all the data is stored with some level of redundancy. So you can imagine that the data is stored on a virtual ring, and this ring is divided into different chunks. And for example, the chunk number 1 is stored on node X and node Y. And the problem that the load balancing solves is the problem of determining which nodes contains some specific piece of data, which node we should contact when making a query. So let's see that working. So when we do a basic select query to some particular partition, what happens underneath is that we calculate a hash of that partition key, and that hash determines the position on the ring, and that in turn determines what nodes will be contacted. So let's think of a very basic load balancing policy that we can implement. The naive load balancing policy that we could implement, that is a round-robin policy, is a policy of first we send the data, the query, to the first node, then we send it to the second node. If there was a third node that contained the data, we would send it to the third node, and then we send it back to the first node, the second node, and so on. So this is a very basic load balancing policy. We maintain a simple integer counter, and when we send a query, we just read the counter, and then we increment it after each operation. If we exceed the number of replicas, we bump it back to 0, and that way, when we send many requests, the load will be balanced equally between all the nodes. A more basic version of that would be to just every time randomize a replica to send the query to. However, in some languages, actually randomizing a number might be a pretty costly operation compared to just incrementing a number. So this is one aspect that is forced in that algorithm, as well as we only have some statistical guarantees that after a large number of queries, the load will be balanced, but in some small period of time, it might be a bit unbalanced. It seems like those algorithms should be all it takes to have load balancing in the driver. How hard could it be, one might think. However, when you try those algorithms in practice, you very quickly see some problems. So let's start with some very common example. And this example happens when one of the nodes in the cluster happens to be slower compared to other nodes. This might be to some hardware limitation. Maybe the disk is slightly slower due to pure luck, or maybe the network happens to be faulty for some reason, or the node became temporarily overloaded because of a number of queries performed to that node. Even if that node has only 10 milliseconds more latency, that will really poorly affect the P99 latencies of the entire cluster. In ScyllaDB specifically, the problem might be even worse. In ScyllaDB, we store the data in each core separately. So we share the data between cores. And when we look at a specific core, that core is not as powerful as the whole machine. And if there's even a small spike in request to that particular core, that core could become overloaded. So in that case, the problem might be even worse. This is an example of the data that we have collected in our benchmarks. So this data shows how many requests are waiting to be processed on a particular node and particular shard. And as you can see, this is a fairly low number. Maybe 30 requests are waiting to be processed at some particular moment of the time. However, what's most problematic in that graph that you can see is that there are certain spikes of number of in-flight requests. And that suggests that a particular shard was a bit overloaded for some period of time. As this graph only shows a couple of minutes of the data, this spike wasn't really that long. It was maybe a couple of seconds, but when you combine all of those spikes, they can really affect the overall P99 latency. And what's problematic about those spikes is that they are on different shards. It's not like a single shard has those spikes. It happens all over different shards. And those spikes are transient. They don't happen for a long time. They happen for a very short period of time. They are really unpredictable. And this really makes it really complicated to design a load balancing policy to solve that problem. On this graph, we have recorded some strange behavior that we actually didn't really even expect to see. So this is a similar graph to the previous graph, but in this graph you can see some strange periodicity. So for some period of time, the number of in-flight requests is low, and then in a sense coordinated, all of the shards have a large number of in-flight requests. It quickly spikes, and then it goes back down after some period of time. And actually, we didn't expect that behavior. This is one of the earlier tests that we did, and this really tells the lesson to us that we should really watch out for those behaviors, and we should really think about if there are some problems that could cause simultaneous degradation in all of the clients at the same time. Having collected all those data, we wanted to do some synthetic scenario that would really show one of the problems with those basic algorithms of load balancing. So in this particular test, we have started a medium-sized Scylla cluster, 5 nodes of i3 4x large. Each of the nodes has 16 vCPUs, and we purposefully overloaded a single core on one of the nodes. So this is a medium-sized node, so overloading only a single core. This is only 1/80th of the cluster. It's below 2% of the cluster. So you could expect that the result of this operation wouldn't really matter. However, when we actually measured the problems and different statistics, the results were really staggering, and this had a great impact on the cluster. So this is a graph of different statistics, overall statistics of the cluster. And as you can see, in that scenario, the P99 latencies of the cluster were really horrible. The read latencies were 200 milliseconds, even though the average latencies were pretty low. As you can see, having a single overloaded shard can have a really great impact on the whole cluster. This is going into more detail about the state of the cluster. As you can see, one of the shards is severely overloaded. It has 100% load, while other shards are pretty much idling. They are below 25%. In that scenario, we have used a naive round-robin policy, and as you can see, all of the shards receive a similar number of requests per second, even though one of the shards is really struggling with the load. And when you look at the latencies, we see that this particular shard is really causing a problem. It has really large latencies. When we look at the different statistics from the driver's perspective, from the client's perspective, we can see that this shard has so many in-flight requests on that connection. So the connection to that particular shard has nearly 500 requests that are waiting at some period of time to be processed. And actually the 500 number is the limit that the driver imposes, and it starts to time out all the other requests that are happening at the same time. But if you look at the bottom, all of the other shards have a low number of in-flight requests. It is well below 100. In the top graph, we can see that the driver is sending the requests equally to all of the shards. So one solution that you can think of is to always send the request to the least loaded node, the least loaded shard. This will work well. However, if you have many clients, this could introduce a thundering herd problem. In that problem, all of the clients see that one particular node is the least loaded node. They try to send all the requests to that least loaded node. The least loaded node now has so many requests that it becomes overloaded, and all of the clients now see, oh, this node is now overloaded, and they try to send the request to another node. This another node now becomes overloaded, and the issue persists forever. A solution for that issue is to use the power of two choices algorithm. This is a very simple algorithm, but it aims to ignore the slowest replica, so solving the problem that we have posed in our scenario. And this algorithm avoids the problem of overloading the same node by many clients. The algorithm is very simple. We randomize two replicas, and we just select the replica that is more healthy, the replica that has a fewer number of in-flight requests. Those are the similar graphs that I've shown previous, but with a newer algorithm, with this algorithm that I have just presented. So as you can see, the number of in-flight requests is now much lower. So previously it was nearing 500, but now all of the shards have less than 25 requests in flight. When we look at the topmost graph, this is a number of requests that are sent to a particular shard. We see that the algorithm deprioritizes some shard, and this is the shard that we have artificially overloaded, and it sends pretty much the same number of requests to all other shards. And thanks to this, the overloaded shard doesn't really affect negatively the entire cluster. If we look at the comparison before and after, the difference is staggering. And if we look at top level statistics, now we have 5 times more requests per second, and the P99 latencies are well below 1 millisecond, not 200 milliseconds as it was the case before. One other optimization that we have worked on is a pretty fun one. It seems super counterintuitive, but actually it seems to work pretty nicely. This optimization, when it detects some particular shard is overloaded, it sends it to another shard on that same node. What happens underneath is that the processing of the request that doesn't have to occur on the correct shard is performed on the wrong shard, and then the wrong shard moves the processing to the correct shard. So in fact, what happens is that the correct shard is now less loaded because it doesn't have to do the initial processing, and it only has to do the really necessary things that that can't happen on other shards. So this might sound counterintuitive, but in fact it really alleviates the problems. This is a graph of how many requests per second are performed, and the first bump shows how many requests per second could be achieved when we send the request to a wrong shard. This shard was not overloaded, while the correct shard was overloaded. And when we send the request to the wrong shard, we could achieve over 200,000 operations per second. But if we send all the requests to the correct shard, which was overloaded, we could achieve only 100,000 operations per second. So as you can see, sometimes maybe it's better to send the query to the wrong node, and that wrong node, that wrong shard, can do some processing and reduce the load of the correct shard. Now moving on to some interesting practical real-world applications. So many of our users, customers, run Scylla in the cloud, AWS cloud, Azure, GCP, and all of those clouds have some cost of sending the data between availability zones. So all of those major clouds have a cost of 1 cent per gigabyte. One thing to consider in that case is to, in a sense, simplify the load balancing policy and always send the request to the replica in the local AZ, the nearest replica. However, you have to keep in mind that if we always send the request to the local replica, it might become more overloaded compared to when we have 3 choices, for example. So this is not a problem that has a single magic solution. You have to find a trade-off between latencies and saving cost. Finally, load balancing is ScyllaDB driver. We have performed some optimizations in this driver to reduce the number of allocations, as we saw that reading the ring and determining which of the node contain the data is really painful, and it really requires a lot of processing. So we optimize the number of allocations and atomic operations that happen while determining the node that's to send the query to. We do some pre-computation of the data, and as a result, we really optimize the number of allocations and number of operations that happen during this process. So as you can see, there are almost 60% less allocations and 84% fewer bytes are allocated when performing a query. Thank you for your attention, and it was great to present this talk.